Okay, but I guess we need to go ahead and get started. We have two officers from the SPS alumni of this class, of course, and Ms. Burns is president, Mr. Tremblay who's treasurer, and they're here to once again encourage you to attend the chapter of the SPS. Nice active chapter that we have here in this department.
Hi guys, like he said, my name is Kelly. I'm really sorry to come and talk to you last semester, but I think Luke came in to talk to y'all along with the previous president, Jalon. So I was the vice president last semester, but Jalon Averett got study abroad acceptance in London. So that's where he is, so I've taken over as the current president. Alumni of this class, really great class. But so I just want to talk to y'all. I just want to talk to y'all a little bit about what SPS does and kind of get y'all interested because we're really looking to get more freshmen into the group and also get y'all in there for next year so that we can have a really good sophomore class going on. So SPS is the Society of Physics Students here at Clemson. You don't have to be a physics major to join. It's really just a group that is that has an excitement, a love of physics, of science. One of the main things that we do is outreach. So we go to a lot of middle schools, a lot of high schools, and do demonstrations. Liquid nitrogen is always a favorite. If you all have ever seen us do the liquid nitrogen ice cream, that's probably a favorite of people's. But it's not really in the demonstrations that we do. It's really about reaching out to the younger kids and getting them interested early in physics and in science. We also try to do a lot of events. We're currently planning on having a catapult competition between departments, so like mechanical engineering, a bunch of the engineering departments, pretty much any department that wants to join, that's kind of on our works. It's also just a really good organization for studying together. So, I mean, we've all been in this class. We know how trying this class can be. But in SPS, there's a lot of people who have taken this class before, have taken classes that you're going to be taking next year. And it's a really good place to have people, kind of help you through the process. Moral support, look at your homework with you, study for tests. Do y'all still do the recitation sessions?
Tomorrow night?
Yeah, so recitation sessions. If you go in there and then you come next door and you're like, he's done, but I kind of need some more time. Can you come look at this? The handful of people in there who will definitely not just like can help you, but really, really want to help you because we all want to see you also succeed. Because it's about the department. So really, the Society of Physics Students is about progressing physics and progressing the department as a whole, and really kind of getting our name out there. So, anything else?
In addition to the academic help, kind of what Kelly's mentioned, SPS is a very social club. We do a lot of things that are focused on science, but it's also about bringing everyone else together, especially people of common interests. Now, I'm assuming that like 99% of the people in this class are physics majors, so you already have that in common. But the thing that's sort of contradictory about this major is people would assume that people who are physics majors are kind of antisocial. But what you've probably already noticed from your first semester is working together is a big advantage on your homework and the classwork even for studying. So having that social connection with people who have already been through this and with each other is just one more way to unite you guys.
And it's also a really good way to meet people from like your upcoming years that you're going to be taking classes with, and you can help sophomore, junior, senior year in all of these classes.
In addition to that, we are probably going to plan on doing another event that we usually do in the fall, but we kind of got late on this year. We call it USERPA. It's where undergraduates talk about the research that they're doing with their professors in the department, and it's mainly to get you guys motivated to start looking at what you guys want to do in the department, because getting involved in research, for me personally, has really kept me motivated in my classwork, because I know that if I hadn't gotten involved in research, I would have really gotten bogged down with a lot of the classes and lost sight of why I was doing this major, because it does get really hard after this year. But doing research helps me see, okay, this is what my end goal is, this is what I want to be doing. And you can flip around to different professors and try different things, and you get to see what other people are doing, so you see what professors in the department are studying, and there's a lot of different variation of research being done.
So So USERPA that he talked about is undergraduate students in physics research, something like that. And normally we would have just one night of USERPA and a bunch of undergrads would present their things. What I'm kind of looking at doing, what we're kind of talking about doing, is at business meetings. So twice a month we would have one undergraduate present 10 minutes in our business meeting. And like you said, it's a really great way to see what professors are doing and go, oh, he's just a sophomore and he's doing research, I could totally do that. So it's a really good motivator too. So yeah, so that's kind of what SPS is about. Also for, I don't know if there are any more females in here, but for you two, we also have a women in physics group, which we meet once or twice a month and have lunch and kind of talk about, like yesterday we talked about the Women in Physics conference that we went to. And we're always looking for more people. So let me know if you're interested and I can put your name on an email list for Amber, who's one of the graduate students, because we'd love to see y'all come. And if there are any guys who are interested in women in physics, it sounds weird, but I think that's really important for guys to kind of be part of that movement as well. So yeah, so let me know. So the next part, it's a question for y'all. Because we would really like to see y'all being interested in SPS, so what could we do? Does anybody have any like requests or suggestions that we could do to kind of make it more inviting or make it look more exciting? Because y'all are really what we're aiming at. So does anybody have any like, I wish you had a sign outside your door, or I wish, if blah blah blah, I would walk in the door more. Does anybody have any of that?
As an addendum to that question, our meetings are currently on Thursday nights at 7, so tomorrow night at 7 is our next business meeting. If you guys can't come to that because you have a lab or something like that,
Or a recitation.
Or a recitation. That's right, yeah.
then those are the kinds of things that if we know about, we can help plan around that to make it more convenient for you guys to show up.
Yeah, the common exams, remember, are on Thursday evening, so it might, if you move the business meeting to another night, it might help.
Yeah, so that was kind of what we picked in the beginning because most of us were upperclassmen, but we can definitely look at moving them. Yeah.
Did you explain the difference between business and social meetings?
So the question was the difference between business and social meetings. So we have two types of meetings, and we switch every other week. Business meetings, we talk about, get this, business. Try to. Elections coming up, events that we want to plan, things like that. Social meetings, everybody just comes together, really not formal at all. Plays games, works on homework, things like that in the lounge, and we kind of swap those around. So I can give someone my email. There's no whiteboard in here. But if y'all are interested, and Luke is our treasurer, I forgot to mention that, and Miles is our secretary. So all of our 3 out of 4 officers are in here right now. So yeah, just talk to one of us. I can write my email down somewhere and let me know if you're interested.
Also, follow us on OrgSync if you want to get any information about meetings or events that we're having, anything else like that.
So I have these two nifty like SPS prizes. Does anyone want one? Yes, you raised your hand first. I think I have one left.
But
I'm gonna have to
Give
go
it
with the
out,
woman.
yeah.
Okay. Yeah, I think that's like a laptop decal or something like that. But yeah, definitely come join us at SPS. We'd be really excited to have y'all. Does anybody have any last minute questions so I don't take up any more of this time?
Do you just meet in the physics lounge?
Where do we meet? That's a perfect question. Okay. Done. So our lounge, the classroom that y'all were in last semester on the first floor, right next to the office, you would just come out of the classroom, down the hallway, it's the very next door on the left. So, and we normally have some sort of sign out there. If not, just look inside if it looks like there's a bunch of people playing video games. That's probably it. So, or working on homework and stuff like that. So yeah, so that's where we would meet in the lounge. Anybody have any last minute questions? Okay, well, it was really good talking to y'all. I'll give someone my email. I can give Dr. Doe my email, and he can get it to y'all if that's something that y'all want. Okay? All right. Thank y'all.
Thanks.
Dr. Doe.
Thank you. Okay, let's get down to work. All right, so we're have a recitation tomorrow evening, 6 to 8 in the conference room. and I would like to see 100% attendance at this. It's not required, but I think those who come do find it helpful, and you can spend your time, drop in, spend a few minutes, whatever. I'll have some problems for you to work and some challenge problems after you do those if you really want to get some good work in. Okay, and then let's see here. So we're working on Gauss's theorem, Gauss's law, and the relationship to Maxwell's first equation. So let's begin with a reminder here of the definition, the fundamental definition of the divergence. So the fundamental definition of the divergence of a field is the limit as the volume goes to zero, it shrinks to zero, of the integral of that field over a surface bounding that volume. So we're looking at the flux going out of that surface and then shrink wrap that surface down to a limiting point. So this is very much like a derivative, except extended now to 3 dimensions and covering for a field and not just a function. Okay, in Cartesian form, so this is the fundamental definition. In Cartesian form, the divergence of J is the derivative of each component with respect to that direction, to the coordinate in that direction. So in 3 dimensions, it's the derivative of Jx with respect to x plus derivative of Jy with respect to y plus the derivative of Jz with respect to z. Yes, sir, Mr. Luker.
And this is a scalar quantity.
Yes, exactly right. It's a scalar. There's no direction associated with it. Exactly right. So, and you can also write this as the dot product of the del operator with the vector field, which helps to see more clearly that it's a scalar because it's a dot product. And the del operator is often written in this fashion. So this would be the Cartesian form of the del operator, but we're also combining that with the Cartesian form of the vector field J in that form. Okay, so today's homework covered some examples, 2 simple examples in 2 dimensions. If you have a field that looks like this, that looks like a diverging field. Let's take the divergence of that. And so we get the derivative of the x component with respect to the x direction and the derivative of the y component with respect to the y coordinate, rather, and that's just 2. Notice that this divergence is the same everywhere. It's uniform. Remember, this is a function of x, y, and z. But in this case, it's just a constant. The divergence is the same. For this particular field, the divergence is the same everywhere. So we're going to study this some more. How, for example, another simple field would be to take x hat plus y hat, divide by the distance. And the divergence of this field is not the same everywhere. It's not uniform. Okay, so that would be, in fact, I should put that into the homework. Evaluate the divergence of this function to see that it's different. And this will be dependent on x and y. It's not going to be the same everywhere. So that means in that case, if you were in that one that in your homework you have this field, I'm sorry, I should do a better drawing of it. Let me start over again. This is back to that example in the homework, x hat plus y hat. If I draw this, make a sketch of this field, it's increasing with distance in proportion to the distance. So the magnitude of this is just r, right? It's square root of x squared plus y squared. And so as you get farther away from the origin, this field is increasing like this. Okay? Now, in order to get a flow like that, if you're imagining that this is the flow pattern of water on a surface, in order to get a flow pattern like this, you're going to have a source of water dripping down on this thing, streaming down on this, and in fact it will have to cover that whole area uniformly. The source has to be distributed uniformly over this. That's what the divergence is telling you. that there's a source of fluid uniformly distributed over the surface, and that's why it's expanding outward like it is. Whereas this other one, which would be, for example, this would be a different example over the square root of x squared plus y squared. In that case, the flow vectors have the same length all over, and that would mean there's a different distribution of the source. Another one would be over x squared plus y squared. Again, now in this case, the vectors get very large at the origin and die off as you get farther away. These will have different distributions of the sources. The source will be different. In this case, there's a uniform divergence, and that means that the source of this flow is the same everywhere. Okay, we're going to we'll be doing more examples, so you'll see more and more of this and understand what I'm talking about more clearly. The other case was this rotational. Let's see, was it y x hat minus x? The sign doesn't matter. The divergence of this field is 0, and that's a circulating field looking, let's see here, looking like this. It goes in this direction. And in this case, the magnitude of this field is increasing the farther away you get from the origin. But the divergence of this field is 0 everywhere. There's no divergence. You cannot generate this field by pouring water straight down and trying to get flow like that. You have to stir it in some way, but that's a different kind of flow. Okay, now let's consider Gauss's theorem from Gauss's from the fundamental definition of the divergence. In the textbook, he derives the Cartesian form by taking the Cartesian form of the divergence by taking a very small cube and calculating the divergence on that very small cube and taking the limit. Then he demonstrates how to derive the Cartesian form from taking our surface to be a cube, right? In this definition up here, this surface can be any shape. This volume could have any shape. For the purposes of figuring the Cartesian form, he uses a small cube. All right, now let's then the divergence is take the flux through that cube, the surface of that cube, and then to divide by the volume. Okay. What if we were to take a second cube and put it with the two faces touching, say along the x face, like that? If we were to calculate the total flux through the combined surface, that is through this combined, combined two cubes together have an outer face, still 6 faces, but what happens to those two inner faces? Well, they're not counted if we're calculating the flux through the outer surface of those two combined two cubes. But we could consider that the flux out of this is equal to the flux through the first volume plus the flux through the second volume. In other words, that this would be S1 J dot dA plus S2 J dot dA. How does that work? Okay, well, in this case, you're calculating the flux out of all of these faces. That is, there are still 6 faces, but it's an elongated, right? It's a rectangular solid now. In this case, we have the same faces. There's 6 on this one. But what's different is that these two interior faces that are touching, going to be brought together now, will also be included here in these, right? So when we're doing this one, we have 6 faces on this cube, and when we're doing this one, we have 6 faces on this cube. When we bring them together, 2 of those faces are touching, and those will cancel each other, because what is coming out of one through that face is going into 2 through the other face. Let's look at the area element here. The area, whoops, didn't want that. The area element here on 1, drawing a little bit bigger picture, the area element here is pointed this way, and the area element here is pointed that way, right? So dA1 here is the negative of dA2 over here. They're opposite directions, same magnitude, opposite directions, But if we have doesn't matter what direction the flow vector is in, what is counted as coming out of 1 is going to be counted as going into 2. Those have opposite sign and will simply cancel. So when you bring those two cubes together, the faces touch, the fluxes cancel, and all you've got is the outer surface that's remaining. All the interior surfaces exactly cancel. They touch, and they exactly cancel out. So the interior surfaces cancel. Now you could keep doing that. Let me keep adding more cubes. I have, oops, oh, there we go. I have a cube, and I put another cube next to it, and I put another cube next to it, and I put another cube next to that, and I could extend it in other directions. I could extend it downward. And every time I do that, the touching faces cancel. So when I combine all of those cubes, what's left is the outer surface of this collection. And that's why that total outer surface there, the total flux out of that outer surface, is the volume integral of the divergence of J. Because I'm adding all these cubes, each one of them gives me a divergence. When I add them all together, I get simply the inner surfaces cancel, and I get the outer surfaces, all that remains. So this, because it's in 3 dimensions, there's more to it, but fundamentally it's very similar to the fundamental theorem of calculus, which, remember, going back to that, you just add up the increments and you get the total increment over the distance. If I'm walking from here to Greenville, at each step I'll move uphill, I'll go higher altitude or lower altitude. If I just keep track of all those increments, that will give me then, add them all up, I'll get the total altitude difference between here and Greenville. That's really all that's included. It's just, we're talking about now in terms of a vector field and a volume integral and a surface integral. So it looks richer, it is, but it's basically the same idea. Okay, so this is Gauss's theorem. And so I'm hoping from that explanation you can see the relationship between the volume integral and the surface integral that's contained in Gauss's theorem. Okay, now Gauss's law is very similar to this, and but it deals with the electric field and the relationship between the electric field and the source of the electric field, the cause of the electric field being charge, that is a charged body, and then a distribution of that charged body. So we have then 2 forms of Gauss's law. 2 forms. There's an integral form and a differential form. Gauss's law deals strictly with the relationship between the electric field and the charge density. The integral form is that the flux of the electric field coming out of a surface is then 4 pi times the charge enclosed in that volume, right? Enclosed by the surface. Remember, we're talking about a completely enclosing surface. There's going to be some volume, and I look for the total charge inside. Now, that charge is a net charge. So I have both positive, the possibility of both positive and negative charges. And that charge enclosed here is the net. Now, the differential form is the divergence of the electric field is 4 pi times the charge density. And that charge density, remember, is a charge per unit volume, but over a very small area. So I have an increment of charge and an increment of volume, and I take the limit as delta V goes to 0. And that's my charge density.
What is a subscript of Q again?
Yeah, okay, hang on a second. So this is rho is the limit as delta V goes to 0. It's a charge per volume. That subscript there, enclosed by the surface there. It's what's inside the volume. Now these 2 forms are related to each other by Gauss's theorem. You should be able to see that. If I integrate, say, the differential form, let me take the integral over the volume of the divergence of E. then that should be 4 pi times the integral of rho over the volume. So if I'm adding up the charge density over the volume, I just get the total charge inside the volume, right? So this is 4 pi times Q enclosed. Remember, the charge density can be positive or negative. It's because I have possibly positive and negative charges distributed over some volume. Of course, when I talk about charges, I mean substances with charge. So, but you understand the shorthand I'm using. Okay, now by Gauss's theorem, this volume integral can be related to the surface integral. This is Gauss's theorem now. And that's how I go from the differential form to the integral form of Gauss's law. Okay, now these two are then the same. That is, they're related in by Gauss's theorem, but they're the same physical content, namely that the charge is what causes the electric field, and the electric field, in the manner that we've talked about, causes the alteration of the plana and the parts of the plana neighboring the charge, and it propagates outward, right? We've talked about that. So this is, in fact, another way of expressing Coulomb's law. Doesn't look very clear, but it's all in there. This is Coulomb's law written in a different way. Remember, Coulomb's law was the electric field from a point charge. It's just proportional to the charge, falls off like 1 over the square of the distance. So 1 over the square of the distance, that inverse square force, that inverse square law, that behavior is incorporated into this. It's in there. Okay, now the other thing is that this differential form is what you often see as Maxwell's first law. Maxwell's first equation, excuse me, Maxwell's first equation. Of course, Maxwell had lots of equations, but what we're talking about, equations in electricity and magnetism. We're going to have 4 of Maxwell's laws. This is the first one in its version. And remember that this is applying the case of electrostatics. Remember that. This chapter is dealing only with stationary charge. Now, you can extend this, so that's the electrostatic condition, stationary charge. Now, this can be extended approximately to a case where the charges are moving, if the charges are not moving very fast, namely that the distance involved is short enough that you don't have to worry about the propagation. The time of propagation is negligible. So you can extend the electrostatic, what would be called the electrostatic approximation. That says that the propagation time is negligible. And you can use the electrostatic form, electrostatic equations apply approximately. And so you can just use them as though the propagation time were negligible and things are instantaneous. Okay? So there's the electrostatic condition. Strictly speaking, nobody moves. The electrostatic approximation is, well, they're moving slow enough and the distances involved are short enough that I can treat it as though they were static. That is, so the field, if the charge is moving, here's the charge with its field. If the charge moves over here, then I instantaneously treat the field as though it moved over there with the charge. Okay, that's the electrostatic approximation. Okay. Okay, so Gauss's law is very interesting. Let's consider some of the consequences of Gauss's law, Maxwell's first equation. So if I have a charge centered, here's a charge, and I'm going to put an imaginary surface around it. An imaginary sphere in this case. Let's begin with an imaginary sphere. Now, that is Maxwell's first equation, written in integral form, is going to allow us to find the electric field in this case, which is actually something we already know, right? We already know how the electric field behaves, but let's go back to the integral form of Gauss's law, Maxwell's first equation, the flux of the electric field is 4 pi times the charge enclosed. Well, in this case, there's only one charge enclosed. It's the one at the middle. And this imaginary surface that we put around it is a sphere. And it's centered on the charge. Okay, now we're going to go from this using this very simple, very symmetric arrangement. We're going to show something. Makes it very easy to demonstrate what the electric field should be like around this using Gauss's law. Okay, so the argument is that by symmetry, E points radially, either radially inward or outward. It has no component tangential. Now, how do we make that argument? Well, let's suppose I consider a point here on the surface of that sphere and draw a line from the center out through that, penetrates out, and let's make that an axis of rotation. Okay, now close your eyes. I'm going to rotate that thing by some amount. I'm not going to tell you how much. And then you're going to open your eyes again. Now, you can't tell that I've done anything because the charge itself doesn't look like there's been no change in the placements of the charges if I rotate around that axis. If the electric field were to have some component in, say, that direction, but you close your eyes and now I rotate the charge, you open your eyes, you don't know whether I've rotated it or not, or by how much. So why would the electric field be in that direction, right? It could, if I rotate the thing, shouldn't the electric field rotate? Okay, so that argument tells you there can be no component of the electric field except radial, inward or outward, because that would be unchanged by a rotation around that axis. Does that argument make sense? There's no feature of the charge distribution that would allow you to have an electric field pointing in any direction other than straight out or straight in. Okay, so that's the first thing by symmetry. E must be radially outward. The second thing is that E, the magnitude, is uniform over the surface. And that's because every point is the same distance from the origin, from the charge. And so it's uniform. Okay, so that allows us now to evaluate this integral without really knowing very much calculus, without having to do the integral very much. This integral, E dot dA, we just said that E is radially outward or inward, so let's suppose it's outward. And E is parallel to dA. dA points radially outward because we're talking about a sphere. So E and dA are parallel. The dot product just gives you E and dA. That's from 1, first assumption. The second assumption is that I could pull E outside of the integral because it's the same for all area elements. And so this is now just an integral. I'm just adding up all of the area elements, which gives me the total area of the sphere, 4 pi r squared. Okay, well that tells me, and that's going to be equal to 4 pi q. So that gives me then that E is q over r squared. Okay, so in other words, you can see Coulomb's law is related to this, right? Coulomb's law gives me that the electric field is q r hat over r squared. And so very closely related to this. The 1 over r squared force law is buried, it's in here, inside of this. Oop, it's inside of this. This is possible only because of the 1 over r squared force law. Okay, so what you're going to do is to extend this argument now. This is your homework. You're going to extend this argument to other surfaces, other shapes. One of them will be to say, take a line charge. There we go, a line. I'm going to take a long line. I'm going to put charge on it uniformly along that line. And now I'm going to have a charge density, lambda, which is a charge per unit length. I'm going to distribute the charge uniformly on this line. And now I'm going to surround this again by an imaginary surface. And I'm going to look at the flux through that imaginary surface and figure out how much charge is enclosed in that. So what kind of surface, imaginary surface, I can pick any one I want, would be convenient in terms of the symmetry of this line? A cylinder. I want to surround it with a cylinder, concentric, right? I want to align the axis of the cylinder with that line. So I'm going to pick an imaginary surface that looks like this. And I want to be far away from the ends. For this argument to work, you have to be far from the ends of this line. So you have to be far from the ends of the line and close to the line. And here's the reason why. You'll see why. But I'm going to use Gauss's law now. I'm going to calculate the flux of the electric field, and I'm going to see that I'm going to use Gauss's law here in this integral form, Maxwell's first equation, and the charge enclosed. Well, how much is the charge enclosed? If this has length little l, how much charge is enclosed? I've distributed the charge uniformly over the line, so it's the fraction of the charge, which is in proportion to little l over big L. Right? So in other words, you could say it's the total charge here, total, here's the total, times little l over big L. Right? That just says it's the proportion here. And you'll recognize that this is equal to lambda L. Your Q tot over big L is just the linear charge density. So this is called the linear charge density. Okay, so the length of that imaginary cylinder will determine how much charge is enclosed, not the radius. The radius is not relevant for determining how much charge is enclosed, simply the length of the cylinder. All right, now let's do the surface integral. Now here comes the symmetry argument again. How should the electric field be pointing? Can it have any component parallel to the line? And that would be because, close your eyes, I might flip the line like that. And the charge hasn't, the charge distribution looks the same before or after that operation. If it had some component of the electric field parallel to the line, and I flip the line, shouldn't the electric field also flip? But you can't tell whether I flipped it or not. Therefore, there can be no component of the electric field parallel to the line. So the symmetry argument here, by symmetry, E points radially outward from the line. Right? So it's keep hitting the wrong thing there. It points radially outward like this. Looking top down, it's just pointing radially outward from the line. And it's going to be the same. Well, okay, we got. I'm getting ahead of myself here. That's the first thing to notice. Okay. Now, when you're doing your homework, I want you to spell out this argument here, the symmetry argument. I want you to be very clear. Spell it all out, just like I'm doing here. This argument. In fact, a little bit more than I've written down here, what I'm saying. I want you to write down. Okay. Because the symmetry argument is necessary. This doesn't work. If the symmetry argument doesn't work, then this doesn't help. Okay. Now, but let's look at that surface integral. And remember, we're integrating over a cylinder. Well, how many faces are in that shape? There's three. Two end caps, and then what would you call it? The cylindrical surface of the cylinder. What is that called? The belt, the band, whatever. This outer, this part. Okay, so we have three different faces: two caps, two end caps, and then the belt. Let's say. Okay, end cap 1 plus end cap 2. These are both surface integrals. They're not closed surfaces, though, right? They're pieces of a closed surface, so they're not closed surfaces. And then finally, the belt. Okay, what is the flux through the end cap 1? What is the flux through that end cap? Surface area elements point which way for that cap?
Perpendicular.
Yeah, along the line. right, along the wire, along the line. And which way is the electric field?
Radially outward.
Radially outward, so that there's no flux through that end cap. It's all coming out through the belt. Neither end cap has any flux, right? Both of those are 0. These are both 0 because of 1 here. There's no flux coming out the ends of that little box, that little cylinder. And so it all comes out through the belt. And in fact, what are the direction of those area elements around the belt? Well, those are radially outward. So again, E is parallel to A. And here we go, the same argument again. E is now uniform over the surface of that belt. That would be the second part. E is uniform over the belt. So this is just then E times the area of the belt. Okay, if R is the radius and L is the height of the cylinder, what is the area of the belt?
Circumference times little l.
Right, the circumference of the circle, 2 pi r, times the thickness of the belt, the height of the belt. So the area of that belt is 2 pi rl. Okay, so let's put it all together here. 2 pi rle, that's the flux, is equal to 4 pi times the charge enclosed, which was lambda L. The L's cancel, pi's cancel, so E is equal to 2 lambda over R. So the electric field is going like 1 over R. Didn't we find that result already before? Do you remember we did this early on, right at the beginning of chapter 2, well, maybe it was 1 or 2. I've forgotten exactly where we did it. Simple homework. We were just looking at how this surface expands, right? The E field is being the influence is being dissipated over a larger surface area, and from a line charge, then it goes like 1 over distance, right? Okay, so this is, again, consistent with that same thing. It's just a different way of getting the same result. Okay, you're also going to look at a plate. Okay, but notice in this argument, by the way, I need to point out, we have to make this clear. We're far from the ends, because if we were close to one of the ends, the symmetry argument doesn't hold anymore. Because if I flip the line now, it's flipped, right? Or another way of looking at it is if you look at the electric field from a line like this, near the center it's going to come radially outward, but near the ends it's going to come at some funny angle. So this argument that the electric field is radial holds only in a region that's close to the middle and far from the ends. And so that's got to be stated in this, that you're far from the ends and close to the middle. In other words, R is much, much less than L. That little box, that little cylinder we're drawing has to be in tight to the line. You can't be way out here, because then it may not be radial. It may get flux through the end caps is what happens. You might get flux through the end caps. Okay, so the argument holds. So you have to be clear about this. This is a beautiful way of getting the electric field for different geometries, but it only works in a really highly symmetric case. So let me point out what happens if it's not highly symmetric. Let's go back to our charge again. What if we put an imaginary surface that's off to one side? Okay, what does Gauss's law say? Well, the flux is still the same. The flux hasn't changed. How can that be? I've shifted the sphere over, but the electric flux of the electric field coming through that hasn't changed. It's the same. Well, you can think of it, we go back to the fluid analogy, it's coming out, it's got to go through somewhere, so it's got nowhere else to go, right? It has to come out. But the details are kind of interesting, because the electric field here is stronger here than it is over here. It's not uniform over the surface anymore. And in fact, it's pointed over here at some funny angle, so it's not normal to the surface. It's at a funny angle. Okay, so if your integral calculus is good, you could actually do this integral. It's a little tricky. It's not bad, but it's obviously not as simple as the one we just did, where the sphere is centered on the charge, right? Remember, this is an imaginary surface. I can put it anywhere I want. Okay, so that's a problem in calculus for you to do. He actually discusses something very much like this in Chapter 8, PFR Mechanics, when we're talking about gravity, because that also has a 1 over r squared law. So you might go back and review that if you want to try this. The amazing thing is that integral doesn't depend on where the charge is inside the sphere. In fact, it doesn't depend on it being a sphere. Well, I shouldn't have done that. Okay, we're going to get rid of that. Let's keep the surfaces kind of simple here. That's my timer here. Okay, here we go. Flux is the same. What if I put a positive and a negative charge here, plus Q and a minus Q? Suppose I put a dipole inside. What's the flux through that surface?
The combined.
Yeah. The combined electric field. What's the flux of the combined electric field? 0. It's amazingly simple, isn't it? It only matters what the total charge is. Now, to prove this, it takes a little bit of work. I mean, this is what the content of Gauss's law and Gauss's theorem combined with this. It's very much dependent on the 1 over r squared force, 1 over r squared law, that the electric field diminishes like 1 over the square of the distance. If that weren't true, then this statement that I just made wouldn't be true. It's very dependent on that. Okay, well, what if we put a charge outside? What if we draw our surface outside? Here's plus Q, and we have a surface over here. What's the flux through that surface? 0. There's nothing inside it. No charge inside, right? Okay, but there's an electric field present. How does the total flux through that surface come out 0? Okay, we have electric field here, and it's weaker over here, and it's over here like this, and it's over here like this. Okay, now I add up the flux over that whole surface. Well, some of it is positive and some of it is negative. What's this piece of flux? Is it positive or negative?
Negative.
It's negative, right? Because the surface area element points outward from the volume that I've constructed. So that's negative. Over here, is it positive or negative? Positive. In fact, I get just as much positive as negative, because if I think of this as flow, and I have this bounding surface, and I have this flow, but there's no charge inside that generates additional flow, right? Using this analogy of flow, it's going to come in and go out. What comes in has to go out somewhere else, because there's nothing inside to generate more flow or to act as a sink. So the integral over this is 0, because there's no enclosed charge. Very interesting. So what happens if we move that surface? We start off with the charge inside, and we move the surface, and we move it so that the charge is now outside. It's like that. As long as the charge is inside, the flux is 4 pi q. When it moves outside, it's 0. It's a step. It goes bump like that. Of course, now what we're considering here is kind of an extreme abstraction, that our charge is a point-like thing, and the surface is infinitesimally thin. So it's either inside or out, right? I mean, that's an extreme abstraction. Physical bodies don't act like that, but we're doing mathematically, we can have that abstraction. Okay. So one more that I want to do here. Let's take a charge here, and I'm going to define a kind of a peculiar surface here. I'm going to have 2 concentric spheres, and I want to consider the volume bounded between those 2 spheres. This is the volume I'm talking about. So it has 2 bounding surfaces. There's an inner surface and an outer surface. And when I do my surface, when I'm calculating the flux, I've got the flux coming out of that volume. So I have to add the flux going this way and the flux going that way. I have to add those together. Okay, so here's a challenge. what is going to be the integral of that, where I have two spheres, different radii, both, and let's make it simple, let's make them all concentric to that point. What's going to be the flux through that? It's zero. There's no charge enclosed inside of this volume. Okay, well, let's check that out. Let's go back. Now, we've done the outer one already, right? That was one we did earlier. The flux through the outer surface, let's say flux. Through the outer sphere was 4 pi q. Remember, we figured it was 4 pi q. It was, remember, it's E, which is q over r squared, times the surface area, which is 4 pi r squared, and so it's 4 pi q. Okay? Doesn't depend on the radius, does it? The flux coming out of that outer sphere is independent of the radius. How about that inner one? Well, what's the direction of the electric field? It's now inward. Excuse me. The electric field is not inward. Erase that. The electric field is outward. But what is the direction of the area element? It's now inward. So this is going to be, it's going to be q over r squared, 4 pi r squared, but a negative sign there because E is opposite, is anti-parallel to dA. And so the result